So what is a random variable? Well, a random variable is just a number that is the result of some experiment. So we perform some experiment and we get a number. Some of the classic types of experiments to talk about when talking about events associated with random variables is the act of flipping a coin. So you flip a coin, and depending on whether it's heads or tails, you write down 1 or 0. So every time you flip a coin, you're essentially generating a random variable, which is a number. Another example is rolling a dice. Every time you roll a die, whatever the number is on the side of the die that is face up is a number that you would write down. So by performing experiments, in this case rolling a dice, you get numbers generated for each experiment. Experiments that are more applicable to the material we're studying in terms of analyzing digital communication systems are some of these following examples. For instance, we are interested in things like the probability of correctly receiving a bit. If I am transmitting information representing bits from point A to point B, I would like to know what the probability of those bits arriving correctly at point B. So that is an example of the types of probabilities and random quantities that we'll be looking at in this class. Another probability that might be applicable in a communication scenario is wireless link fading. We talked about fading channels earlier in the class. A wireless channel fade is a fluctuation in the received power level at the receiver. If the power level fades or goes down too much, receiving the transmitted signal is a difficult thing to do. So we might be interested in what is the probability that my wireless channel fade exceeds some number. Maybe it fades by more than 10 dB or more than 20 dB. That probability is something that we'll be interested in computing, and in a sense is a random quantity. Every time we transmit a piece of information, the random variable, or number in this case, is the amount of the fade. Sometimes it's a reduction in 20 dB, sometimes it's a reduction in 10 dB, but it's a number, it's a random number. Other examples that we'll be interested in are sample values of a noisy signal. If I'm transmitting a signal and it gets corrupted with noise at my receiver, when I sample that signal and want to write down a value of my sampled signal, what is that value? When everything was deterministic, that was an easy thing to do because I knew exactly what I was transmitting. But now that noise has been added on top of it, we don't know what that number is going to be. So every time I sample, I'm really getting a random variable and I'm writing down a number that is a random quantity. So these are all examples of random variables. The first couple are kind of the classic things you look at when you start studying random variables. The last few are examples of things that we will be interested in as we study digital communication schemes. So let's talk about some basic terminology associated with random variables. The first term that we're going to get familiar with is the idea of the sample space. The sample space, and that's something we typically denote as this S, is the set of all possible outcomes. So in the example of flipping a coin, there are only 2 outcomes. Either you get heads or you get tails. So for a coin, the sample space is pretty simple. It consists of 2 things, heads or tails. What about when rolling a dice? Well, when you roll a dice, there are 6 possible options. You either get 1, 2, 3, 4, 5, or 6. This is actually a picture of the sample space for a die here on the bottom. We've denoted S as the sample space, and there are 6 things inside the sample space. The event where I roll the dice and get a 1, the event where I roll a dice and get a 2, the event where I roll a dice and get a 3, etc. So each of these dots inside the sample space that are labeled zeta 1, zeta 2, zeta 3, all the way through zeta 6, those correspond to the possible outcomes that I can have during my experiment. So this is the sample space. What is the event? An event is just a subspace of S. So here is S, and subset just means part of S. So as a specific example, let's talk about the event an even number was rolled. So I roll the dice and I get an even number. So even numbers are 2, 4, and 6 on dice. So this right here, this oval, represents the event when I roll an even number because it's zeta 2, zeta 4, and zeta 6. Those are all the ways that I can roll an even number, and that collection of events is a subset of S. What about the event me rolling the dice and getting a number greater than or equal to 3? Well, I have indicated that event here as G3. I've put a box around all the different experiment outcomes that make up the event getting a number greater than or equal to 3. That's when I roll a 3, a 4, a 5, or a 6. So events are just subsets of the sample space. So these are the kind of the classic things to draw when you're dealing with simple things like flipping coins or rolling dice. For the examples that we're concerned about in this class, the sample spaces are a little different because the values that our sample space can take on are often much larger. Heads and tails, those are only 2 possible values, and so there's only 2 points in the sample space. Rolling a die, there's only 6 possible values, so the sample space only has 6 discrete values. What about when we sample a noisy signal? Well, usually that means we can get any value between minus infinity and infinity, so that has a much larger sample space. So as we get into some of the more practical examples for our systems, and things that we're concerned with, the sample spaces will be a little bit more complicated, but the concept is the same. The sample space is just a set of all possible outcomes, and an event, something like rolling a dice and getting a number greater than 3, or sampling a signal and having its value greater than 5, those are still just subsets of the sample space. So an event, in terms of a random variable, is just a subset of the sample space. So an event is really just a set. Some of the set operations that we'll be concerned with are depicted here. This is a picture depicting the complement of a set. So if my sample space is S, that means every experiment I do always is inside of S. Here is the event A. The complement of A, which we denote as A raised to the C, just consists of all the points in the sample space that aren't in A. So this white region consists of all the sample points inside our sample space that aren't in A. So that's what we call the complement of a set. In the middle picture, we have 2 events depicted. We have event A and we have event B. And the operation that's depicted there is the union. The union is just the combination of A and B. So what we've depicted here is the union of A and B. So this is a collection of all the points inside the sample space that are either in A or in B. And we use the notation, this kind of cup symbol, this capital U, and we read that A union B. On the far right, we talk about the intersection of events. So again, we still have 2 events, A and an event B, inside of our sample space, but what we're depicting in this figure is the intersection of these events. This small kind of elliptical region right there, which the arrow is pointing to, that is the set A intersect B, and it consists of all the points inside the sample space that are in A and in B. So a union is an OR. A union B means in A or in B. A intersect B is an AND operation. It means events that are in A and in B. If we had events A and B that didn't have any overlap, then we would call those events mutually exclusive. Another name for mutually exclusive events is disjoint events. When working with disjoint events, their intersection is the empty set. They don't have any common area, so when you try to find a set of points that are in both A and B, there aren't any, so that is just the empty set. What we're working towards is being able to compute the probability of an event. For instance, I want to compute the probability that my link fade got worse than 20 dB. So that might be an event that I want to know what the probability of that occurring is. So what we really need to be able to do is to be able to compute the probability of events, and one way to do that is through an approach called relative frequency. And that's what this chart explains. So we're going to let n be the number of experiments I perform. So in the case of rolling a dice again, just rolling dice n times. We're going to let n of A denote the number of times event A occurs. So if my event was the event I get 3 or greater, every time I roll the dice and I get the number 3, 4, 5, or 6, I would add that to this counter. And after I've rolled my dice a total of n times, n of A is the number of times that the outcome had a dice value greater than or equal to 3. Using these 2 quantities, we can define the probability of an event A as follows. The notation we use is P of A, and we read this as the probability of event A occurring. And using relative frequency, we write this as a limiting operation. We say as limit as n goes to infinity, so as the number of experiments that I perform gets very large, I let the probability of event A equal the ratio of the number of times event A occurred divided by the number of experiments I performed. And this kind of agrees with our intuition. If I roll the dice a whole bunch of times, say 1,000, and write down the number of times I got a value greater than or equal to 3, that ratio is a pretty good estimate of the probability of the event getting a dice value greater than or equal to 3 occurring. So this agrees with our intuition. And obviously, from just looking at this, we can see that these probabilities are bounded how we think they should be. If I have n of a equal to 0, the probability of a is 0. On the other extreme, what happens if the event A occurs every time I roll the dice or perform the experiment? In that case, the event A occurred n times, and I would have n over n is equal to 1. So we obviously have that the probability of an event is always greater than or equal to 0 and always less than or equal to 1. So we just use relative frequency to compute the probability of an event occurring. We can use a similar approach to compute the probability of conditional events. So conditional events look like this in terms of probability here at the bottom, and we'll get to how this equation comes to be true at the bottom. But basically what we're wanting to do is compute the probability of an event B given that the event A has happened. And that's what this notation means here with the B vertical bar A. The probability of event B given that A has happened. So we want to come up with this equation right here at the bottom. So let's go ahead and figure out how we're going to do that. As before, we're going to let capital N be the number of experiments performed, and N1 is going to be the number of times event A occurs out of the capital N trials or N experiments. We're going to let N2 be the number of times event B occurs out of the N1 times. So N2 is out of N1, not capital N. And what we're going to do here is we're going to compute first the probability of A and B occurring. Okay, so that probability, when we use our relative frequency approach, is the limit as the number of experiments goes to infinity of N2 over capital N, because this ratio accounts for the fact that A has occurred and B has occurred, because N2 is the number of times that event B occurs out of N1. Okay, so we have this limit of this ratio right here. In this second step, what have I done? All I've done is multiplied by 1. I put an N1 on the numerator, and I put an N1 on the denominator. And the reason we write it like this is because now this first term, we've seen that. That's really the probability of A, because that's the number of times event A occurred out of capital N. And this quantity right here, N2 out of N1, that is this new quantity that we're defining, the probability that B occurred given that A occurred. And that's exactly what this ratio is. N1 is the number of times that event A occurred, and N2 is the number of times that B occurred when A occurred. So that's exactly what this ratio N2 over N1 represents. So we now have an equation. The probability of A intersect B is equal to the probability of A times the probability of B given A. So if we just use algebra, we can solve for this term, probability of B given A, and write it in this form here on the bottom of the page. So we can compute conditional probabilities of events, things like what's the probability that B happens given that A has already happened, in this very nice form right here. On the previous slide, we computed the probability of B given A. We could have done a very similar sequence of steps to compute the probability of A given B, and it would have looked like this. And then we would have had two equations, the probability of A given B and the probability of B given A, and we could have combined those to yield these equations right here. And these are what are known as Bayes' rule, and it lets us compute conditional probabilities of events as a function of the other conditional probability. So you can see P of A given B is a function of P of B given A, as well as just the probability of the events themselves, P of A and P of B. So these are some expressions that we'll see often when you deal with probability. They're called Bayes' rule. They're especially useful when you want to do computations of events that impact each other. When these things, for instance, something like drawing cards out of a deck without replacement. What's the probability that I draw an ace given that I've already drawn these cards? Computations like that. We want to now talk about some special types of events, and these are independent events. Events A and B are independent if and only if, that's what this IFF means. They're independent if and only if the probability of their intersection is equal to the product of their individual probabilities. If the probability of A intersect B is equal to the probability of A times the probability of B. So when we're dealing with independent events A and B, this equation holds. Or, because it's an if and only if statement, that's a two-way condition, if I can write the probabilities this way, then A and B are independent events. So if you go back to the previous slide and substitute P of A given B, P of A intersect B is equal to P of A times P of B, things simplify quite a bit. It turns out, when we go back and look at Bayes' rule, for the case of independent events, these conditional probabilities simplify. P of B given A is just P of B, and P of A given B is just P of A. And that kind of makes sense. If the event A is independent of B, then A should have no impact on the probability of event B occurring, and that's exactly what this equation says right here. Similarly, if event B is independent of A, event B should have no impact on the probability of event A occurring, and that's exactly what this equation says right here. Given that event B has occurred, how does that impact the probability of A? Well, it doesn't. Probability of A is exactly equal to the probability of A given B. One thing to be careful about here, and students mess this up quite a bit, independent and mutually exclusive are very different things. Independent is this definition right here. It says that the probability of their intersection is just the probability of their individual probabilities multiplied, and that these conditional probabilities are just equal to the probabilities of the events themselves. Mutually exclusive means probability is zero. And that's a very different thing than it factoring into individual probabilities. So be careful with that. Independent and mutually exclusive events are very different things, and don't mix those up. Let's talk about that just a little bit more. Mutually exclusive events cannot occur at the same time. They have this relationship right here. So the probability of A and B, meaning both event A and B have occurred, that probability is zero. If we're dealing with a set of mutually exclusive events, so maybe we have event A1, event A2, event A3, if they're all mutually exclusive, we have a very nice result. Basically, the probability of A1 or A2 or A3 or A4, etc., the probability of one of those occurring, because they're mutually exclusive and only one can occur, if any, the probability of their union is just a sum of their probabilities, because any of the cross terms, there is no overlap. All these cross terms are zero. So when dealing with mutually exclusive events, probability of union simplifies dramatically in just this nice sum. And again, this warning point here on the bottom, independent and mutually exclusive, they sound similar, but they do mean very different things. So just keep that in mind when you're working problems that use either this term or this term. Make sure you're using the appropriate definition. When you're working with mutually exclusive events, that means their intersection has zero probability. When you're working with independent events, that means their intersection is equal to the probability of A times the probability of B. The total probability theorem lets us compute probabilities by enumerating over all the different conditional ways that it can occur. That probably doesn't make a lot of sense right now, but let's look at a picture about that. So let's consider some sample space. So assume that this rectangle here is my entire sample space, and it's been partitioned into a whole bunch of disjoint events. So there's event A1, there's event A2, there's event A3, A4, A5, and A6. And these are disjoint or mutually exclusive events because they don't overlap. This square, A1, does not overlap with the square A2, and A2 does not overlap with A3, and A2 does not overlap with A5. They are mutually exclusive or disjoint. They don't overlap with each other at all. Let's say that I want to compute the probability of B occurring, where B we're going to visualize as this ellipse here. So to compute the probability of B, how can I do that? Well, the way we're going to do it when we think about it in terms of disjoint events and this total probability theorem is on the following slide. So how are we going to compute the probability of B? Remember, B is the ellipse in the previous slide. The total probability theorem says that we can compute P of B as this sum. We can sum up over all the disjoint events AI, and in each of these terms, what we compute is the probability of B given AI times the probability of AI. So for the picture we drew just a minute ago, this is the probability of B given A1 times the probability of A1, plus the probability of B given A2 times the probability of A2, plus ... all the way up to the probability of B given A6 times the probability of A6. And the reason this works is because the A sub I are disjoint and they completely divide up the sample space S. So let's do a proof of why this works. I want to compute P of B. P of B is nothing more than our event B intersected with the sample space S. That was the picture we drew on the previous slide. The way we have selected the A's perfectly divide up the sample space S. So if I union A1 with A2 with A3 with A6, what do I get? I get out the sample space. So all we've done is replace the sample space S with this union of A's, which is completely equivalent. So at this point I have the probability of B intersected with this set of unions here. Well, guess what? Intersection is a distributive quantity, so I can distribute my intersection across each of these terms. So instead of writing it as B intersected with this union of unions here, I can write it as B intersect A1 unioned with B intersect A2 unioned with ... B intersected with AN. Specifically in our case, the figure we showed on the previous slide, N was 6, so this would go all the way up to B intersected A6 for the little cartoon that we drew. And now look at this. I have B intersected A1 union B intersected A2 ... What do we just say about mutually exclusive events? This right here is mutually exclusive from this right here, which is mutually exclusive from this right here. This is just a little piece of the oval. This is just a little piece of the ellipse. This is just a little piece of the ellipse. Each one of these pieces, if we go back to that cartoon that we drew, is mutually exclusive of the other. And we know that when we take the probability of a union of mutually exclusive events, that's just equal to the sum. So instead of a union of things, I just have to sum up over a set of P of B intersected with AI. So each of these comes right here, and we have equality here specifically because each one of these events is mutually exclusive. From here to here, what have I done? I just used our conditional probability expression. We know that we can write the probability of B intersected AI as the probability of B given AI times the probability of AI. So this is known as the total probability theorem, and as long as we partitioned our sample space up into a set of disjoint events that completely covered the sample space, that was important here, right? We had to be able to write S as the union of all these A's. As long as that's true, I can compute B in this manner. And this is a useful thing that we'll do in various problems. So we've had two important results. One we call the total probability theorem, and one that we called Bayes' rule. If we put these both together, we obtain what we call Bayes' theorem. As before, we assume that we have this set of disjoint events, A1 through AN, so they're mutually exclusive or mutually disjoint, and they partition the sample space. And by partition the sample space, we mean that they completely cover the sample space S perfectly, just like we drew in our cartoon a minute ago, where S was a rectangle and the A's were just these little squares that perfectly covered that rectangle. Bayes' theorem says the following: the probability of A sub j given B is equal to this. This is just Bayes' rule. We did this earlier. If I use the total probability theorem now on Bayes' rule, what does that say that we need to do? It says that we write P sub B as not just P sub B, but as this sum. That was what we just did for the total probability theorem. We said we can compute P sub B as a sum over all the disjoint events AI. So Bayes' theorem is this piece right here. The probability of A sub j given B is equal to this expression right here. That's what we mean by Bayes' theorem. And it really just follows from writing down Bayes' rule and then applying our total probability theorem to the denominator P sub B. And again, this is something useful that we'll use as we do different probabilistic computations in the course. So we've been talking about events. The last type of event that I want to talk about is having to do with Bernoulli trials. So Bernoulli trials are basically experiments that we repeat over and over. We assume that each event each experiment or trial is an independent experiment. And what we're looking for is something happening during each of these trials or experiments. When that event A, which is what we're looking for, occurs, we say that we have a success. and when it doesn't, we say that we have a failure. So the simple example again is flipping a coin. If I'm flipping a coin over and over and over and over, that's my trial or experiment. If I'm looking for heads, every time a heads occurs, I would say I have a success, and every time I see a tails, I would say I have a failure. The probability of seeing a head or having a success is what I call P. If success is P, then failure has to be 1 minus P because they have to add to 1, and the notation we use for failure is Q. So that's the notation we're using. The probability of having K successes in a specific order in N trials is this expression right here. So for instance, maybe N is equal to 5, and I want to know what the probability of seeing the sequence head, head, tail, tail, tail is. Well, I could plug into this equation if I knew what the probability of flipping a head was, and I could compute the probability of seeing that exact sequence of outcomes. If I'm not as concerned with a specific sequence of outcomes, I just want to know maybe what's the probability of having K successes in N trials, I use this equation. So this equation has that probability in it, but it has an extra factor out front. This we read as N choose K, and this just accounts for all the different ways that we can have K successes out of N trials. For instance, if I'm just concerned with computing the number of times I have 2 heads out of 5 trials, well, 2 heads can occur out of 5 a lot of different ways. The first 2 can be heads, the first and the last can be heads, the second and third flips could have been heads, the second and fourth flips could have been heads. There's lots of ways that could have occurred. This term right here, N choose K, which is equal to N factorial over K factorial times the difference N minus K factorial. This accounts for all the different ways that that can occur. For our class, we're usually not concerned with flipping heads or rolling dice or anything like that, but this is still a very useful equation. Maybe I'm concerned with transmitting bits. Maybe I have 1,000 bits to transmit. The probability of successfully receiving a bit is 0.99. Maybe I want to know what the probability of transmitting all of those bits successfully is, all of them. Or maybe I want to know what's the probability of 90% of them being transmitted reliably, given I have some probability of bit error rate on each individual bit. So this concept of Bernoulli trials and this equation down here in particular lets us do those type of simple computations. To wrap up this section on events, we're going to work a few examples. One example will be on conditional probability. Another example will be very much a comms related problem. We'll look at a problem on what's called the binary symmetric channel, or the BSC. And finally, we'll work a problem on repeat coding. Again, this example here is very specific to digital communications. We'll look at that, and each one of these examples will be explored in its own video to follow.